Let's starting our last but not the least talk of today.
Okay, thank you. So today I will talk about low-end obfuscation and learning. This is a joint work with Alec Boyle, Yuval and Robert, and Pierre. So first of all, what is program obfuscation? What is the intuitive goal behind program obfuscation? So we want to hide the implementation of a program while preserving the functionality. So here you can see an example that I took from the internet about some program. You can try to guess what the program was before this happened to it. Yeah, so it just some website from the internet. It obviously comes with no guarantees whatsoever. But this is the original program, it just computes the Fibonacci numbers. I also tried to use ChatGPT and ask it to obfuscate the program, but it really didn't work. It gave me something that is just wrong. It outputs numbers that are not the Fibonacci numbers, and I'm not sure if it's that obfuscated. It's wrong on both ways. Sorry. It's not that I got yeah, so obfuscation to preserve functionality. Okay, so yeah.
Obfuscating.
I mean, obfuscating. Yeah.
You just didn't interpret it in the right programming language. Reinterpret all the symbols.
Yeah. I mean, we can change the definition, so ChatGPT will work. You know? Yeah, because we love it so much. Yeah. Okay, so ideally, what we want is some notion of virtual black box obfuscation. That is, we don't want the obfuscated code to reveal more information than a black box access. Unfortunately, this notion doesn't exist. It's impossible to obtain virtual black box obfuscation, as proven by a paper, like pretty old one from 2001. And it led to coming up with a few various notions of obfuscation, and the most common one in the literature is indistinguishability obfuscation. And the overall or the informal definition of indistinguishability obfuscation is a probabilistic polynomial time algorithm, such that for every two pairs of programs that computes the same thing, that they're functionally equivalent and of the same size, we have the distribution of the I/O on the first circuit is indistinguishable from the I/O on the second circuit. And here I didn't specify two things, right? I didn't tell you what program means, and I didn't tell you what indistinguishability means, right? So we will build it now. So here on the y-axis, you can see different notions of programs, right? We can have decision trees, we can have 3 CNFs, and of course we can have the most general notion of Boolean circuits. And we can have, on the x-axis, we have different notions of indistinguishability. We have computational indistinguishability, we have statistical and perfect, and I will go over it soon. Here, yeah, okay. So the standard notion of indistinguishability obfuscation in the literature usually refers to, mostly refers to computational obfuscation of Boolean circuits. Okay, so this is where it stands. So let's see what is the definition of computational indistinguishability. So essentially what it means, okay, so I included all kinds of crypto definitions here because I assume the cryptographers will not be here because I have a deadline today. But I have been told that the deadline passed, so I don't know, maybe they did arrive.
As of half an hour ago.
Half an hour, okay, yeah, so my joke doesn't work anymore, but that's okay.
What do you know if the server is still open?
Okay, so two ensembles of distributions are, let's start with computationally indistinguishable. If every polynomial size circuit family cannot distinguish between the two distributions, and the advantage, the distinguishing advantage is negligible. And in the notion of statistical indistinguishability is the same, except here we don't limit the size of the circuit family, the distinguishers. And perfect indistinguishability means just that the two distributions are the same. Okay, so this notion of indistinguishability obfuscation has many applications in the literature, starting from deniable encryption, optimal multi-parity computation, hardness of finding Nash equilibrium, and also in this workshop it has been mentioned in different contexts. So we heard about I/O and its application, but has a lot of application. This is a partial list. Okay, so a natural question is, does computational I/O exist? So first, if you're in algorithmica, if P equals NP, then yes, it's very simple to construct obfuscation. We just pick, you give me a circuit, I'm just going to pick the lexicographically first equivalent program for circuit, right? If P equals NP, I can do it, and it's very easy. And in heuristica, does I/O exist? And the answer is no. This is a work by Moni and others that show that if NP is not in infinitely often BPP and I/O exists, then we can construct one-way function. Okay, and this argument also rules out Pessyland, right? The existence of I/O in Pessyland. Okay, and what happens in minicrypt is the answer is also no, because if you give me an I/O and a one-way function, we can construct public key encryption. In fact, even in this talk later today, I will show similar ideas about how to construct public key encryption for these two objects. And in Cryptomania++, probably yes, we have good evidence that it exists. There are recent works from 2001 and 2002 that constructed obfuscation for general circuits using well-studied computational assumptions. Okay, and now does statistical I/O exist? And probably not here. Okay, so here what happens is that above this line, deciding equivalence of programs is co-NP hard. Okay, and if you're in this area, then unless the polynomial hierarchy collapses, we cannot do statistical obfuscation. And the idea is that we can use the randomness of the I/O as a short proof for equivalence of programs. So if you're here and equivalence is co-NP hard, we cannot do statistical obfuscation. And our work is here in this area. So we're going to talk about statistical obfuscation for weak models in the sense that we can test equivalence quickly. And we will also talk about a notion of computational obfuscation for simple program classes like 3CNF that we cannot hope to get statistical I/O for 3CNF, but we will still ask if they're simple in some sense that I will define soon. Computational obfuscation for 3CNFs. Okay, so this is our work. We're going to deal with weak classes, weak representation classes, and we will try to get strong guarantees, strong security guarantees, and we'll call it the low-end regime versus the high-end regime, which appears in the literature, where we have strong program classes, usually general Boolean circuits, and we get weak or weaker guarantees. Right? We get only computational indistinguishability. So why doing it, right? Like why asking these questions, this type of questions? So first, the first answer is that if we want to achieve any notion of information-theoretic security, we must settle for weaker models of computation, right? Because what I just said, we cannot have statistical security in a stronger models of computation. And a natural example in this case is, can we obfuscate decision trees, right? We can check equivalence of decision trees quickly. So the lower bound that I just said doesn't work. And can we obfuscate them? Information theoretic. And another example is that if we want to obfuscate simple functions, can we obfuscate them in a way that preserves the representation? So can we take a 3CNF, obfuscate it computationally, but I want the output of the obfuscation to be a 3CNF. And of course, we can always do high-end obfuscation. We can always run the algorithms in the literature. But the right question is why to do it, right? If we have a decision tree or a 3CNF, then we really don't want to obfuscate it by a circuit because it just adds complexity. The representation is much more complex. Also in practice, usually we prefer simpler representation. It appears in the literature, in the learning literature all the time, the distinction between proper and improper learning algorithm, precisely for those reasons. And we ask, why not here?
Of course, you can say interpretable, explainable, whatever.
Yeah, we can. Yeah. But this work is not. It's just about proper and improper. It's the first step if you want. Okay, and another good reason is that if you good reason not to use the high-end obfuscation is that if you restrict ourselves to weak program classes, we can get stronger guarantees using simpler algorithms. One example from the literature is with OBDDs, that we can get a much stronger security guarantee than computational indistinguishability, and the algorithm is much simpler than the general obfuscation that appears in the literature. Okay, so the high-level summary of our results is first I'm going to show positive results using white box learning, which is a learning model that I will define. We will also prove negative result using PAC learning, negative result on proper obfuscation. And finally, we're going to separate a few variants of information-theoretic I/O. And of course, I will define them when we get there. But it's important to see that we achieve both negative and positive results using learning. Different notions of learning, of course, but using the idea of learning.
In particular, you're able to obfuscate things which you don't know how to learn, or where get it wrong. So, are you able to obfuscate classes where we don't have a PAC learning algorithm?
Yeah, so this is a good question. So we will define the learning model that is much more general than the PAC learning model or exact learning model. It allows you to do more things. So for now, it is open. We don't have really a good example, but it is plausible that we can obfuscate things that we cannot learn.
But you don't have a separating example, like something that we don't know how to learn, but you can write, but you can do it.
No, but we have things that the usual learning paradigm are more complicated, and our paradigm simplifies. Okay, so first let's talk about the positive result using white box learning. So let's start with a warm-up. If we have a class, a program class that is exact learnable with membership queries. Okay, so what does it mean? It means that I have some learning algorithm. We have a learner, and it interacts with some oracle or someone who knows the function. And membership queries are simply queries of the form, what is the value of f of x? Give me x, what is the value? Given x, what is the value of f of x? Okay, so if we can, if we have an exact learn algorithm that uses membership queries, and it's an exact algorithm, so eventually the learner knows specifically exactly what f is. It's not, there is no notion of approximation here, and we can efficiently implement the membership queries. Right, then in this case, it's natural, it's very easy to see why we can obfuscate. Right, we'll just run the learn algorithm, we'll simulate the membership queries, and since the algorithm, yeah.
Is this only for deterministic algorithms, or?
So it depends what notion of obfuscation you want, right? If your obfuscation is general obfuscation, then no, the learn algorithm doesn't have to be deterministic.
Oh, okay, because it's the same distribution, sorry.
Yeah, because it's the same distribution because the learning algorithm only sees semantic properties. It only sees the value of f of x. It doesn't see f at any point. So there's no reason why it would depend on the representation. Okay, but if you look with more attention to this paradigm, then, well, we don't really need to limit ourselves to membership queries, right? All we need is queries that are efficiently computable, right, from a representation of the function, and that they only depend on the semantic of the function. They don't depend on the representation. So this is naturally leads to the definition of hint function. So what is a hint function for a program class? Just that, basically. It's an efficiently computable property of the class that depends only on the underlying function. And now,
Can't you get something stronger like VBB from this?
No, because VBB requires you to be able to obfuscate anything in the sense of black box. Okay, and here you do reveal some representation. So essentially, it is a question of how much the programs in your program class reveal about a function. Right? Like if I give you a decision tree, for example, I can obfuscate, well, I can, but suppose that we can obfuscate decision trees in this, under this model, right? So you will get a decision tree, and in particular, you will know a lot about the function. You will know about the set of ones, right? Because you can look at the decision tree and you know. Suppose even it's a point function.
But if it's learnable, you could do it by yourself as well, right? By just querying the oracle and learning the tree by yourself.
Yeah, but you do have a representation. Now I'm the obfuscator. I have a representation of the class, and I give you an obfuscated program. If I give you a decision tree, let's suppose that it's a point function. If I give you a decision tree, then obviously you know the point, right? But in a VBB model, if I give you an obfuscated version of a point function, you shouldn't know the point. So that's not VBB. You had a question?
Oh, well, I was just going to say this is somewhat ironic because one of our motivations in introducing obfuscation was to try to show that there are no such properties that can be decided with white box access that can't be decided with black box access.
It is. Okay. So an example of hint functions. Let's go over a few examples. So if I have a decision tree, like I think the conversation we just had really explains this example. But if I have a decision tree, then I can implement equivalence queries, right? And equivalence queries are queries of the form the learner gives the teacher or oracle. Basically, the learner says, I think this is the function. And then the oracle or the teacher says either yes, correct, and then we learned it, or they say no. And if they say no, they produce a counterexample. That is a point on which the two models are different.
Here, if the point they give depends on the decision tree that they have, as not just on the function, but on the decision tree, then you're not necessarily going to be.
Yes, it depends how you implement the hint. The point is that the learning algorithms should work regardless of how you implement the hints. So if you have a learning algorithm that uses one hint that depends, well, it's not a hint because I defined the hint to be oblivious to the representation. But if you have a learning algorithm that learns with queries that depend on the representation, right? It should work by the definition with queries that don't depend. This is exactly hint functions. So you're right. Maybe here I should add that with an equivalence queries that they should be implemented in a way that is oblivious to the decision tree. And you can do it, right? Like you can, it appears 2 slides ahead, but you can, if I give you a decision tree, you can sample a uniform satisfying assignment. And you can give me the first lexicographically satisfying assignment. You can do a lot of things in a decision. Okay, so the one slide I have, not 2 slides. So you can, like I just said, you can sample a uniform satisfying assignment. And this shows why this model of learning is stronger than the usual membership equivalence queries, right? Because this kind of queries, given a uniform satisfying assignment, is not something that we can implement using membership or equivalence queries. So we are allowing a larger set of queries in the learning model, and so it is plausible. It relates to Moni's questions that it is plausible to have classes which we can learn in this model using much more general queries, but we cannot learn under membership equivalence queries. But for now, we're uncertain. We don't have any concrete. Okay, so this is our first result theorem. You have a program class P, and P admits polynomial time IO, perfect IO, right? Here, the notion is statistical and information theoretical. If and only if we can learn P, we can learn the class using exact learning algorithm with hint functions. And why this is if and only if, right? Like that's okay. And before we go to the proof, which is two lines basically, the obfuscation is proper if and only if the learning algorithm is proper. in the sense, the usual sense, proper in the learning literature. Okay, so why this is true? So we can obfuscate just by running the algorithm, right? Like I said before. And the other direction is true because we can use I/O as a hint function. The definition of a hint function is general enough to allow just calling the I/O as a hint. So it's an if and only if, and this model of learning exactly characterizes information-theoretic obfuscation. So if you have some program class and you want to information-theoretic obfuscate it, it's enough to think about learning algorithms in this class, but in a more general model of learning. Okay, so let's see some implications. So before I need to define what is learning in the mistake-bound model. So what is learning in the mistake-bound model? We have a learner that sees the samples in string. So they see x1, x2, x3, etc. And after observing some sample, they need to guess the function or the label, as they call it in the learning literature. So they need to predict C of x for some C. And after every mistake they do, the learner makes some mistake. After every mistake they do, they can update their what they think the hypothesis is. And the goal is to make at most m mistakes on every order of the sample. So the order of the samples is possibly adversarial. Okay, but the goal is still to make at most m mistakes. And it has been known for quite a while that if a concept class can be learned in the mistake-bound model, it can learn using equivalence and membership queries. So if we have a learning algorithm in the mistake-bound model and we can implement equivalence and membership queries efficiently, then we can obfuscate the class, right? It follows from what I just said. And an application of this is quasi-polynomial time canonization algorithm for decision tree. So what we're going to get is an algorithm that canonize. I will define it soon, decision trees. And this result has been known, or quite recently, actually, from 2015. But our paradigm gives a much simpler conceptually way to derive this result. So the second result is negative result using PAC learning. Yeah.
Where does the mistake bound, if there was a mistake bound M, where does that, what does that correspond to in the?
Yes, so the mistake bound. Okay, so if you can learn in the mistake bound model with the parameter M, you can exactly learn using M+1 equivalence or membership queries. So this is where it comes from.
But then, and then when you show
It needs to be
that's equivalent
polynomial.
to obfuscation, then
So your obfuscation algorithm will make M+1 equivalent.
yeah, all right.
Oh, so the second result is negative result.
Sorry, before you got here, can you just summarize what you get for decision trees? I don't know if you said it and I missed it. So
yeah, I can. So there is essentially what you get is an algorithm that runs in quasi-polynomial time that given any decision tree, regardless of its size, is the mean of canonization. It gives you a canonical representation of a decision tree that computes that function. So
and this implies, I'm sorry, this is probably obvious, but this implies I/O for decision trees.
yeah, so it is a much stronger guarantee than
Much stronger guarantee than
I/O.
I/O, right?
Yeah.
Gives you canonical that computes the same. Okay.
Right.
I see.
Yeah, so it is a much stronger
And
guarantee.
could this be done in the quasi-polynomial? The decision tree can have what depth is the tree here?
Yeah, so it actually uses a notion of rank rather than depth. I'm not sure this is
Okay, but so I don't know, is there any bound that you can state in terms of depth of the tree? I mean, what's the running time of this in terms of the depth of the tree?
yeah, I'm not sure. I mean, that depends on your tree. I'm not sure what.
Squared S.
Yeah.
The original thing has size S, then the new one will be like log squared S.
log squares the
Yeah.
time to make canonical.
Yeah. Like the output decision tree will be like S to the log S size, but the depth could be something. The depth could be a bit worse.
Okay, so forget depth. So okay, so is this size? So can you do anything with polynomial size, or it's unknown, or it's like
Yeah, it's unknown.
It's
unknown?
in
Okay.
polynomial time, you mean, to do that?
So I think he said that you can canonize
Oh, I see. Yeah.
with a quasi polynomial blob in the size. Is right?
Yeah.
And,
Yeah.
and you're saying it's not known if you can do it with just a polynomial blob, right?
Yeah, and even more is unknown. Even if you give up the canonization requirement and only require to
IO.
do some statistical perfect
IO.
IO, then it's still unknown.
Unknown if you can do it in polynomial. Okay, I see. Okay.
Sorry, since you're saying so much about it, I still didn't catch what canonization means. What
Okay, so I will say it now, and then later we'll skip the slide. So if you haven't, let's think about perfect IO. So the goal of perfect IO is if you have two programs of the same size that compute the same function, you want the distribution of the IO to be the same on both of them, right? Okay, so now if you have, we can think about a notion of a deterministic IO, which is like an IO, but deterministic. So it maps every two programs of the same size that are equivalent to the same thing. Okay, now we can remove the requirement of having the same size. Okay, so it is a program that maps every two equivalent programs, regardless of their size, to the same thing.
and then what's the runtime?
So it depends on the definition, but you can think about it as polynomial in the input thing. So here's an example for why it's not the same thing, right? Like if you have a program class that has exactly one circuit of every size, but testing equivalence in this class is very difficult, then you trivially have deterministic IO, right? It just like outputs whatever you get, and you're going to be okay because there is only one circuit of a given size in this family. But you cannot canonize because you cannot test equivalence. So it's not, so canonization is a much stronger notion.
The obfuscation here would be improper, right? Because
No, I think it is proper.
the mistake-bound models,
Yeah.
usually the algorithms are improper. And
For decision trees? No, but
no, the application, like if P is learnable, the mistake-bound model doesn't require openness.
right. So, but this is an example. I'm pretty sure it's a proper learning. Okay, so now let's get to the negative result using the path learning. Okay, so now let's talk about 3CNF. So equivalence for 3CNF is co-NP hard, so we cannot hope to get statistical obfuscation. But what about computational proper obfuscation? That is, I want the obfuscator to output also 3CNF. Can we do it? And the answer is no. If one-way functions exist, there is no polynomial time IO computational for 3CNFs by 3CNFs. And we actually proved something a little bit stronger. We proved that we cannot obfuscate 3CNFs to any program class whose dual class is PAC learnable. Okay. What is the dual class? So a dual class of a program class is just a class of inputs and programs. The goal of the role of programs and inputs is being reversed. Okay. So if we have some function eval that evaluates the program P on an input X, right? So here on the left side we have the program class P, right? So we have P hard coded, or we remember it, and we are ready to perform eval on any input that we get. And the dual class is exactly the opposite. We have the input hard coded, we remember the input, and the what we get is a program from the class P. So this is the dual class. Okay, so if the dual class of our program class is PAC learnable, we cannot obfuscate 3CNFs into this class. So it actually proves something a little bit stronger than obfuscating 3CNFs, but 3CNFs, we cannot obfuscate 3CNFs by any order of one 3CNF. We cannot do 3 CNFs to 100 CNFs. It's impossible. And unlike the talk yesterday by Mikito, we know that 3 CNFs are easy to dualize. This is why this theorem is. Okay, so now let's talk about separating variants of I/O. So we had this discussion with Tony, so I'll just do it quickly. Deterministic I/O is just like an I/O when we remove the probabilistic option. It cannot be a probabilistic. And here the indistinguishability is replaced by just equivalence, just the same thing. And the canonizer is a deterministic I/O. So again, we remove the probabilistic and the indistinguishability, but we also remove the requirement of the size of the program. And those are not the same, and I already said it before, so just skip it. Okay, so now let's see another separation. But in this case, we're going to think about some abstraction of the model. So now we have an equivalence relation over binary n-bit strings. And the way we're going to think about this relation is the following. 2 strings are in the relation if and only if they represent the same program. It's a very abstract view about this obfuscation. This is why we call it abstract obfuscation. Okay, so what is a canonizer in this model, in this relation? So given x, the canonizer should return some y in the relation with x. And additionally, we want that for every x and y in the relation, right, the canonizer of x equals the canonizer of y. This is just the definition. Yeah.
So to have an obfuscator, you have to be an equivalence relation.
It just, so yeah, so we can always define this during the equivalence relation if you compute the same function.
Yeah.
So, yeah, so now I just work with this abstract model. Of course, it's a weaker.
Right, but so we should think of the relation that we're given. This is the one example, but it could be an arbitrary equivalence relation like graph isomorphism.
Yeah, you can. Okay, and what is a perfect I/O in this example? It's just an algorithm that you give it a string x and it outputs equivalent, random uniform equivalent member of the equivalence class. Okay, so let's see how to separate canonization and perfect I/O for this type of relation. And we're going to use a function that has random self-reduction. Okay, so it has been mentioned in the workshop before, but I will quickly, just a reminder. So what is a random self-reduction for the function? It's probabilistic polynomial time algorithm sigma, such that on input x, it outputs a uniform element in the same with the same answer to f. And we have examples for such function, but we also need a function that is hard to check if f of x is equal.
So like graph isomorphism.
Yeah, you can think about it. You can also think about it as some sort of encryption. Yeah, but or DDH encryption, right? In DDH encryption, you can, if I give you an encrypted message, you can sample a uniform message that is the same message, essentially, but you cannot test. If you get 2 encrypted messages, you're not supposed to be able to tell if they encrypt the same thing. So it exactly fits to this paradigm. Okay, so in this case, like the examples that we just mentioned, in this case, we can easily create a relation that has perfect I/O, randomized I/O, right? But we cannot canonize, because if we cannot even test equivalence, and we cannot canonize. Yeah, and this is the example of DDH. And the third theorem is a separation between perfect I/O and deterministic, even improper I/O. But it is, you can think about it as in some oracle model. So it is in the common reference string model, and we assume the existence of one-way function, ideal obfuscation. And again, you can think about this separation as a separation in an oracle model. Okay, so now I want to talk about the pack attack with more details. So what is the idea? Okay, what is the idea? So given one-way function and proper I/O for 3 CNFs, we will construct public key encryption, where the decryption circuit, after the secret key is hard-coded in it, is order 1 CNF. Why this is a problem? Because order 1 CNFs can be pack-learned. And that means we can learn the decryption circuit, right, and break the encryption. So we shouldn't be able to do that. Okay, so let's build a public key encryption. So let's take an injective one-way function. The assumption that the function is injective can be removed. And let's take a hardcore predicate for the function and a bit that we want to encrypt. Okay, now what is a hardcore predicate? So I add this, and now I've been told that my joke is no longer relevant because the deadline passed. But a hardcore predicate is a predicate that we can efficiently compute given x, but we cannot given f of x. Okay, so we can just see pictorially what it means. Okay, so let's describe the public key encryption. The secret key will be just a random string and the hardcore predicate on that string. And the public key will just be the evaluation of the one-way function on x. Now, in order to encrypt, we will create a circuit that looks like this, but the circuit computes is f of x equals the public key and the hardcore XOR m. Okay, so we can write a program that computes this function and obfuscate it. So this is the output of the encryption. And in order to decrypt, we will just apply the program that we got, right? The message is essentially a program. It's the result of an I/O on some program. So we can run this program on our secret key and XOR it with the hardcore predicate. And why this is true? Well, just run the program. What the program does is checking if f of x equals f of x, which is true. And I can do it because I have the secret key x. And then there is an and b, which is the hardcore predicate, which again I know because I have the secret key, XOR the bit m that I'm trying to encrypt, and then obviously just m. So the encryption is correct, but let's see why this is also secure. So I have here delta 0. Delta 0 is just the distribution over public key and ciphertext where we encrypt 0. Okay, delta 1 is the same thing except we encrypt 1. And essentially we want to prove that delta 0 is computationally indistinguishable from delta 1. So in order to do it, I will define delta 0 prime and delta 1 prime. And they're going to be delta 0 prime is just going to be the encryption of 0, but conditioned on the hardcore predicate being 0. And the claim is that delta 0 and delta 0 prime are computationally indistinguishable just by the definition of the hardcore predicate, right? What's the difference between delta 0 and delta 0 prime? It's just the answer, potentially the answer of the hardcore predicate, and we shouldn't be able to tell the difference. So they're computationally indistinguishable just by the definition of a hardcore predicate. And delta 0 prime and delta 1 prime, those are indistinguishable because of the obfuscation. And why this is true? Know that delta 0 prime is a distribution over programs that are, or formulas that are unsatisfiable, right? Because we encrypt 0, but the hardcore bit is also 0, which means where's the formula? That those two are equal. So we have an and with a 0. So the entire formula is unsatisfiable in both cases, in both delta 0 prime and delta 1 prime. So both of them actually compute the same function, and they're indistinguishable by the definition of the obfuscator. And what you can see from this proof is that we don't really need to assume I/O. It is enough to assume that there exists a weaker notion that only obfuscates unsatisfiable formulas. This is enough for this proof to work.
Does it give you a general statement of going from IO to PKE? You get a sort of simpler proof, or forget using this? Can you get a simpler proof for showing that IO implies PKE?
So what do you mean by simpler proof? That was kind of simple. I lied here, okay, and I will written in. I lied here because eventually what we want the decryption circuit to be 3 CNF. And here, like you said, it's a general one-way function. No one promises me that it's 3 local. So I essentially lied, and we need to fix it. Okay. And it's not so easy to fix it because when you do the standard conversion to 3 CNF, you're not going to get program that is equivalent, that has the same truth table. You're just going to get equal satisfiability, and it adds auxiliary variable, and it just makes the whole thing into a mess. So it's not that.
But you said that you only had to be indistinguishable for unsatisfiable cases.
Yeah, so that definitely helps.
So if it's unsatisfiable, then when you add this stuff, it's still unsatisfiable.
Yeah, yeah, but you still need to be careful when you prove correctness and security because you add auxiliary variables and things. You just need to be careful, and it's not completely trivial. There's things, computations you need to do, but we can do them, and it works. Yeah, it fixes it. Okay, so now let's talk about some open problems. So first, the natural open problem is what other representation models admit information-theoretic I/O. So for decision trees, for example, we don't know. I think, yeah, it's the next one. We don't know if you have polynomial time, perfect or statistical information-theoretic I/O. The third question is, can we obfuscate 3 CNFs by AC0? And here, just a quick comment. AC0 can be learned over the uniform distribution, but our attack that I just described creates a weird distribution that we need to learn on. So we crucially rely on the fact that we can learn on every distribution in the PAC attack. This is the definition of the PAC learning, right? So being able to learn uniform distribution doesn't mean you can apply this attack. And even 3 as a more general question. So what is the minimal representation class that we can obfuscate 3 CNFs to, right? This work tells us that we cannot do it to any class whose dual is PAC learnable, but it doesn't tell us what we can achieve. So this is an interesting question. And can we separate between information-theoretic notions of I/O using a natural program classes or underplanar assumption? We call that our separation uses some like an oracle model. Okay, it's a bit like this. So can we get it without? These are the open questions you have, and if you have any questions.
Questions? I have a kind of naive question. So this is all about the I/O. How does it translate to other kinds of because there are some results called kind of mixed model.
Yeah, that's a good question. But I don't think the time. Yeah.
Can you say again what were the distributions that you have to learn on in the PAC learning attack?
Yeah, sure. We want to learn. Well, it's not really written here because I lied about the public encryption, but you want to learn the decryption. This thing. So this is the decryption. Where is it? There you go. You want to learn these programs after you bring them to your class. Yeah, so it's not going to be uniform distribution.
So for the negative results, just to make sure I'm following, do you need one-way functions, or can you just assume NP is not in like?
No, you need the public key encryption crucially relies on it. Yeah, when we encrypted, we use one-way function.
But wouldn't like NP not in like BPP and IO give you this, or give you one-way functions, I guess?
So yes, the assumption is NP is not in infinitely often
Yeah.
BPP.
Yeah.
Which is, yeah, but then I mean,
Yeah.
it's like going in circles. If you have one-way function, then you solve them.
Thank you so much.